Okay. Hello, everyone. I welcome you all to today's class. And as promised, our today's class will be on respiratory physiology. So, without any further delay, let's get started. Sorry, not respiratory. Sorry, our today's class will be on renal physiology. We have already finished respiratory physiology. So, renal physiology will start with definitely with the kidney, and we know that kidney has two parts. So the outer portion is called cortex and the inner portion is called medulla. So this is like macroscopically, but if we get into microscopic structure, then this cortex and medulla, they are formed with numerous components, which is um, called nephron, which is a unit, structural and functional unit for kidney. So this nephron is formed by uh, certain parts. So this would include glomeruli. So here you can see uh, this is glomeruli and Bowman's capsule, proximal convoluted tubule, distal convoluted tubule. So glomeruli will start from here, and inside the glomeruli, um, there is Bowman's capsule, and here from Bowman's capsule, there will be starting of proximal convoluted tubule. After the proximal convoluted tubule, we have our loop of Henle, and then we will get the distal convoluted tubule and then collecting tubule or collecting duct. But there is a catch, that is, you can see right here in this picture that there is a demarcation. That this demarcation means this above portion is cortex and the inner portion is medulla. So the outer portion, which is cortex only contains glomeruli, Bowman's capsule, proximal convoluted tubule, and distal convoluted tubule. Loop of Henle usually is present inside the inner medulla, as well as the collecting duct. So the inner medulla will contain collecting duct and loop of Henle. Next, we will move into, so here you can see that inside the cortex, the medulla is formed by some pyramid-like structure, and these are called renal pyramid. There are 10 to 18 pyramids, and this pyramids contains loop of Henle and collecting duct. And after the pyramid, what are the structure we have? Macroscopically. So this is the pyramid. This pyramid will end into minor calyx, and all of the minor calyx will drain into major calyx, and then all the major calyx will drain into the renal pelvis, and ultimately pelvis is a expanded portion and pelvis will be continue as ureter. So this is like very basic renal anatomy. Just wanted to give you some overview. So next, the functional anatomy of kidney. So functional anatomy, there are 10 to 15 million nephron per kidney, and 85% glomeruli are cortical. Cortical means they are present in the cortex. That means they have short loop of Henle. And only 15% of glomeruli are juxtamedullary. That means they are close to medulla with long loop of Henle. So I just showed you this picture. If the loop of Henle is very short, then this nephron will be cortical. But if they're having a long loop of Henle, that means they are deep into the medulla. Next, we will move into a very important recall topic, that is called juxtaglomerular apparatus. So what is juxtaglomerular apparatus? Juxtaglomerular apparatus is made up of few different type of cell. Number one type of cell is called JG cell. JG cell or juxtaglomerular cells. JG cell, it has another name. So either they can give you, either they can, you can call it JG cell, J for juxta, G for glomerular, or it can be called juxtaglomerular cell, or it can be called granular cell as well. And the function of this JG cell or granular cell or juxtaglomerular cell is renin secretion. This is a very important recall topic. So make a note. And so the function is renin secretion, and the location. Location is, it is found in the wall of efferent arteriole, AA, efferent arteriole. I will be discussing about the, so let me discuss here. Okay, so this is a zoom picture of renal glomeruli. So here you can see some capillaries are going inside and some capillaries are coming out of it. So we all know this one is afferent arteriole and this one is efferent arteriole. And here are some capillary network. These are important for filtration or absorption or whatever the function is. So basically we find the JG cell or granular cell where? In the afferent arteriole, exactly right here in the afferent arteriolar cell. Next is macula densa. Macula densa, what is the where is the site? Site of macula densa is between thick ascending limb of loop of Henle and distal tubule. So macula densa is present in the junction of loop of Henle and distal tubule. So where it is? Thick ascending limb. And about a loop of Henle, I want to mention one more thing, that is loop of Henle has some part. So first of loop of Henle has three parts. Okay. So first part is thin descending limb. Second part is thin ascending limb. And third part is thick ascending limb. You can see this one is very thin. Loop of Henle will start from here. So this portion is very thin. So this is thin descending limb. Second part is thin ascending limb. And third part is thick ascending limb. And thick ascending limb has a junction with distal convoluted tubule or DCT. Okay. So macula densa, site of macula densa will be right here, which is the junction between thick ascending limb of loop of Henle and distal tubule. And the function of this type of cell is to respond to change in tubular ion, mainly sodium, and it activates tubuloglomerular feedback mechanism. I will be thoroughly discussing about tubuloglomerular feedback mechanism, but just understand for now, the macula densa is important to sense sodium level in the body, and it will act accordingly. And how it would act, how it would get activated, I will be discussing in the coming slide. But macula densa is responsible for sensing sodium level in the body and act accordingly. Next is extraglomerular mesangial cell. So this extraglomerular mesangial cell, their function is, they are like, their role is not that important. They just provide some structural support. They just exhibit phagocytosis, secrete some hormone like prostaglandin, extracellular matrix, and help regulate the blood flow through contractile. So they are more like supporting cells. But the main cell is JG cell. Function is renin secretion. Very, very important recall. Second main is macula densa. Functioning is tubuloglomerular feedback, or mainly sensing the sodium level in the body. And extraglomerular mesangial cell is just for like the supportive cell. So we are done with the juxtaglomerular apparatus. Now I will move into the Bowman's capsule. So the Bowman's capsule has three layers. First of all, we will discuss about the layers of Bowman's capsule. So in this picture, you can see that the Bowman's capsule has three layers. What are the three layers? This is nothing but just we have done a section, cross section from here. We know that this is Bowman's capsule, right? this outer portion, this portion is Bowman's capsule. So this picture is nothing but just a cross section of this picture. Okay, so I want you to concentrate here. So Bowman's capsule has 3 layers. So from inside to outside, there is no actually from inside to outside, or if we have to say from inside to outside, the most outside portion is this one, this layer, which is the epithelium. So most outside we have epithelium. So this is the epithelium. So there is an interesting fact about this epithelium is that this epithelium has food process. These are like food process or podocytes. So this epithelium contains food process or podocytes. Next, we have the basement membrane in the middle. So this is the basement membrane. And most inside, which is adjacent to the capillary or adjacent to the endothelium, we have our endothelial layer, capillary endothelium. And another fact about this capillary endothelium is they have small, tiny pores. So they have pores between this endothelial cell. So this is the layers of Bowman's capsule. And the function of Bowman's capsule is nothing but just filtration. So it has 3 layers. Most outside is epithelial cell layer, which contains food process of podocyte. Middle, it has basement membrane, and this basement membrane is negatively charged. Basement membrane is formed by negatively charged glycoprotein, and most inside there is capillary endothelium. And the unique thing about this capillary endothelium is they have pores or fenestration. So these are the structure. These are the Bowman's capsule structures. So another thing about the capillary basement membrane is I told you that it is formed by negatively charged glycoprotein. So as it is negatively charged, this basement membrane is negatively charged, and this basement membrane is the main site for ultrafiltration. So this basement membrane actually works like a filter paper. And as it has a negatively charged glycoprotein, so positive charged ion can pass by, but the negative charged ion cannot, because negative and negative will repel, right? So we know that proteins are negatively charged, so protein cannot pass by. For a healthy nephron, protein cannot pass by this basement membrane. But if the nephron, or if the basement membrane is damaged due to some condition like nephrotic syndrome or nephritic syndrome, only then this protein can pass by, and in that situation we call it proteinuria. So lastly, the modified epithelial lining, they have food process like numerous food process like cells, which is called podocytes. Now the function of glomeruli, these are the function of Bowman's capsule. So function of Bowman's capsule is only filtration, because Bowman's capsule is only this portion, okay? But Bowman's capsule plus Bowman's capsule plus all of the tubules will together form what? Will together form glomeruli. And glomeruli, the function of glomeruli, it has 4 functions. It has 4 functions. Filtration, number 1 will be filtration, not secretion. So this is number 1, okay? Filtration, reabsorption, secretion, and excretion. So these are the function of glomeruli. From our kidney, we can do all of these things. We can filter blood, we can reabsorb whatever we need to keep, we can excrete whatever we don't need it, and we secrete certain materials. So these are the function of glomeruli. And glomeruli, filtration. So now filtration will start in the Bowman's capsule, and an ultrafiltrate similar like plasma will enter into the Bowman space. So basically, sorry. So basically, uh, it will start with filtration. I told you the function of glomeruli will start with filtration. So this filtration will start in the Bowman's capsule, and through the afferent arteriole, blood will enter, and blood will bring some plasma or like the blood volume through the afferent arteriole, and through this Bowman's capsule we will filter this blood or filter this plasma, and this plasma will enter into the Bowman space. So it will enter into the Bowman space. It will enter into the through the Bowman's capsule. It will enter into the PCT, then it will enter into the DCT, then it will enter PCT, then enter into the loop, then DCT, then CT, and then it will be end into the efferent arteriole. So this is how it works. Next is the filtration. This is all about filtration. Next is reabsorption. So we will reabsorb whatever we need to keep: water, solute, and secretion. From peritubular capillaries, there are secretion of substance in the lumen, which we will be discussing in coming slide, how this secretion works. And this secretion, this process is done by active transport. So hence it needs energy. Any active transport needs energy. Next is the excretion. Excretion means that substance that is filtered but not completely reabsorbed will get excreted into the urine. Next, what are the factors that is affecting permeability barrier? So factor affecting permeability barrier, because I just told you this, the basement membrane, it is like a filter paper, and all our blood gets filtered through this basement membrane or through this Bowman's capsule. So now the thing is, what are the things that can get filtered and what are the things that will get back, like that is that cannot get filtered through the, cannot pass through the Bowman's capsule. So that factors will depend upon two things. One is the charge, another is the molecular weight. So charge, we have already discussed that the basement membrane is negatively charged, so cations or the positive ions can get easily filtered, but the anions or the negative charge, they cannot. So anion cannot. Next is the molecular weight. So molecular weight is less than, so kDa, this is like a molecular weight of the particle. So bigger particle cannot pass through, smaller particle can pass through. So I have got this two information. In one source, they have written less than 42 kDa. In success, they have given less than 70 kDa. I will suggest you to go with success one, but this is very unlikely that you will get both of them. No, you won't get both of them. So just go with the success one, but still I've got it somewhere, that's why I've put that in the slide. So these two are the factor that affects the permeability barrier: charge and the molecular weight. Charge means what? Since the basement membrane is negatively charged, so negative ion cannot get, negative will repel negative, but the positive can pass by very easily. And the molecular weight, the smaller the molecular weight, the better the permeability is there. If it's less than 70 kDa or 7,000 Da, that molecular weight particle can pass through, but bigger cannot. Next, we'll move into a very important topic, which is GFR, glomerular filtration rate. What do we mean by GFR? So GFR is nothing but the amount of ultrafiltrate produced from plasma flowing through glomerulus per unit time. That means that per unit time, the amount of ultrafiltrate that passes through, ultrafiltrate means what? Ultrafiltrate means the plasma. The portion of plasma that gets filtered through the Bowman's capsule. So the amount of ultrafiltrate that flows through the glomerular per unit time is called GFR. So normal GFR value we need to know. Normal GFR is, it's a recall. So normal GFR is 120 to 125 ml per minute or 180 liter per day. Per unit time means you can either, they can ask it per minute, or they can ask either per day unit. So it's 125 ml per minute or 180 liter per day. And normal, so now this is the GFR, okay? So normal renal plasma flow, you need to memorize this. So normal renal plasma flow is 600 ml per minute. We know that kidney is a highly vascular organ, and the renal artery is very high pressure artery. Why? Because like huge amount of blood is getting passing through the kidney every minute. So you can guess like how much is that. So every minute 600 ml blood is flowing through the kidney, and this is called renal plasma flow or RPF. So we need, why do we need RPF? We need RPF to make the calculation of filtration fraction or FF. So filtration fraction or FF may equal to GFR by RPF. So our GFR was 120 and RPF was 600. So filtration fraction will be 0.2 or 20%. What does this means? 20%. This means that the equation of filtration fraction is GFR by RPF. So if you calculate it, you will get 20%. And also one more thing, total cardiac output. 20% of total cardiac output is given to the kidney. So that is all about filtration fraction. Next, we will move into Starling's equation. So I told you like do this one thing, write all the equations together. I don't know like if any of you have done that or not, but again I will suggest you to do it. Like write all the equation in a single page, so that before exam like you can just take a view, and all the respiratory equations, renal equation, there are not more than 10 equations I think in the whole physiology section. So just write it in a single paper, that would be very helpful. So Starling equation. Starling equation, to understand Starling equation, first we need to understand there are 4 different type of force in the kidney. For that, let me draw a picture of a Bauman's capsule. Wait. Okay. So in the Starling equation, inside a Bauman's capsule, there are 4 different type of source. So different type of force. Two forces will come from the capillary, and 2 force will come from the Bauman's space. So capillary has 2 different force. What are the 2 different force of capillary? This is a capillary, right? This is an afferent arteriole. So it has 2 force. One is hydrostatic pressure and another is oncotic pressure of the capillary. So hydrostatic pressure, what is hydrostatic pressure? Hydrostatic pressure is nothing but the pressure of blood or plasma that is flowing through the afferent arteriole. This is called hydrostatic pressure. So this is the capillary pressure. Another capillary pressure is oncotic pressure. What is oncotic pressure? Oncotic pressure is nothing but the pressure of protein inside the capillary, the amount of protein, because we know that oncotic means protein. So these two are the capillary pressure. And there are similar to pressure in the Bauman's capsule as well, because blood is passing through this capillary and ultimately getting filtered here and passing here. So obviously there are some pressure that is exerting in the Bauman's capillary as well. So in the Bauman's space, so this area is called Bauman space, inside the Bauman space. So this Bauman space has same 2 different type of pressure. One is hydrostatic pressure, another is oncotic pressure. So hydrostatic pressure is the, again, is the flow of the plasma that is getting filtered. So that is exerting a hydrostatic pressure. And another is the oncotic pressure. Now, oncotic pressure in the Bowman space is 0 in a normal nephron. Why? Because we know this, there is a basement membrane right here, and this basement membrane is negatively charged, so protein cannot pass through Bowman space. If it is a healthy nephron, if it's not a nephrotic syndrome or diabetic nephropathy, if it's a healthy nephron, then protein cannot pass beyond this way. So the oncotic pressure of Bowman space is 0. Okay, so these are the values. So hydrostatic pressure of Bowman space is 8 millimeter mercury. Hydrostatic pressure of glomerular capillary is 45 millimeter mercury. Oncotic pressure of Bowman space is 0 because it's negatively charged glycoprotein. It has negatively charged glycoprotein. Protein cannot pass. And oncotic pressure of glomerular capillary is 24 millimeter mercury. Okay. Now, my point is, now if you understand all up to this, then remaining is actually very easy. Now, the thing is, here you can see that the greater pressure is this one. This one is just 8, 24, but the hydrostatic pressure of glomerular capillary is the highest pressure. Why it is the highest pressure? Because I just showed you right here that hydrostatic pressure is what? Hydrostatic pressure is the pressure of the blood that is passing through the afferent arteriole. This is the hydrostatic pressure. So this is the main force that promotes filtration. The hydrostatic pressure of glomerular capillary is the main force that promotes the filtration. So the higher the hydrostatic pressure of glomerular capillary is, the higher the filtration rate, because this is the main force. If there is suppose very high flow blood is going through the afferent arteriole, there will be more filtration. But if there is very low blood supply due to some condition like sepsis or like blood volume loss, so what is going to happen? Blood volume, the hydrostatic pressure is going to drop, and in terms of in resultant, we will get very low filtration rate. So the main point is the hydrostatic pressure of the capillary is the main force for filtration. It's a recall. Okay. Next is the net filtration pressure. So net filtration pressure will be the hydrostatic pressure minus all the pressure. So hydrostatic pressure, why is that? The hydrostatic pressure of the capillary is mainly exerting the pressure to the plasma to get filtered through the Bowman space. But the hydrostatic pressure of the Bowman space is the opposite pressure. Like this is the hydrostatic pressure of the capillary. This is promoting filtration. This is promoting plasma to pass through this layer. But the hydrostatic pressure of Bowman space is the opposite pressure. So it is like opposing the filtration. As well as since this one is 0, the oncotic pressure of the Bowman space is 0. The oncotic pressure, so like you can write 0, but or it doesn't make any sense. So this is why we don't discuss about this pressure, because its value is 0. Now next is the oncotic pressure of glomerular capillary. Oncotic pressure of glomerular capillary is the opposing pressure. Oncotic pressure of glomerular capillary does not help in filtration. It is the opposing pressure. So we will minus that. And this is the net filtration pressure equation. So if you understand till now, then this slide will be like I have already discussed. Hydrostatic pressure is the only force that promotes filtration. This is why we kept it, and we subtracted all other two pressure. And the higher the hydrostatic pressure of glomerular capillary, higher filtration. Oncotic pressure, it will vary with the plasma protein, the amount of plasma protein in the blood, and it is a opposing pressure. Next, hydrostatic pressure of Bowman space, it is also opposing. And the protein or oncotic pressure of the Bowman space, it is zero, because it is a negatively charged glycoprotein, and there is, in this space, there is no protein cannot pass beyond this space, so the pressure is zero, so we don't need to calculate that because it's zero. So that is all about Starling's equation. Next, we will move into the glomerular hydrostatic pressure. So glomerular hydrostatic, before going into that, there is one more equation. We have already discussed this in basic cellular, in recipe, about the flow and the resistance. So flow is Q. In the Poiseuille's law also. In the Poiseuille's law, we have used flow, Q. So flow is equal to equivalent to pressure gradient and inversely proportional to the resistance. That means this is a tube. If there is, I'm giving high pressure, if I am passing some high pressure fluid over this tube, the flow will be higher. But if there is some resistance or some obstruction, the flow will be less. That is like basic physics knowledge. So flow equal to pressure divided by gradient resistance. And this flow determined by three variable. The flow of the we are basically talking about the glomerular flow, right? So it is determined by three variable. One is arterial pressure, afferent arteriolar pressure, efferent arteriolar pressure. So we know that in a Bowman's capsule, we have afferent and efferent arterial. So obviously afferent arteriolar pressure, efferent arteriolar pressure, and overall arterial pressure, like the overall arterial pressure, the blood pressure. We know that if the blood pressure is higher, there is going to be more flow. So these three are the determinants for the glomerular hydrostatic pressure or the flow. Next is blood flows. We know that blood flows from high pressure to low pressure. Glomerular capillary has very high hydrostatic pressure, 45. And this is the reason that glomerular capillaries has very high hydrostatic pressure. This is why there is filtration happens. And when there is an arteriolar vasoconstriction, if there is a this is afferent, this is efferent. If there is a vasoconstriction in the afferent arteriole, what is going to happen? There is going to be increased resistance. Increased resistance means decreased flow. And one more thing I want to show you here, right here. You need to understand this thing. Okay, this is afferent arteriole and this is efferent arteriole. This is afferent and this is efferent arteriole. Now, suppose blood will pass through this, through the afferent. And now suppose there is a vasoconstriction in the afferent arteriole. What is going to happen? What is going to happen to the filtration? If there is a obstruction in the afferent arteriole or vasoconstriction in the afferent arteriole, definitely filtration will drop because blood cannot pass. Blood has to reach into this capillary network, and then there is going to be filtration through this way, right? But if there is a vasoconstriction right here, blood cannot even pass in the first place. So filtration is going to drop. Now, what would happen if there is a obstruction or vasoconstriction is the efferent arteriole? Then what would happen? Then blood will pass through the afferent arteriole very easily. It's passing. It is going through the Bowman space and getting into the Bowman space, but it is not coming out through the efferent arteriole because there is a efferent arteriolar vasoconstriction. So what would happen? So this tube or this afferent and efferent arteriolar network, it is a two-way network. So two-way means what? Blood will go through the afferent and come out through the efferent, but now cannot come out through this way due to the vasoconstriction. So what would happen? Only way is this. Only way is will be in the Bowman space. So the only way blood can escape is this way. So what would happen? If there is efferent arterial constriction, then filtration will increase because blood is not being able to pass through this way. This way is blocked. So it has only this way to pass. So the filtration rate will increase. So if we understand this thing, then pay attention here. That is pressure build up before the point of resistance and pressure decreases after the point of resistance. So if there is a obstruction, efferent arteriolar obstruction, wait. If there is a efferent arteriolar obstruction, then what would happen? Pressure will build up before the point of resistance, like up to here. Just a moment. Suppose this is the efferent arteriolar and obstruction is here. So pressure will build up before the point of obstruction. Before the point of obstruction, all of this capillary network, they will have a pressure buildup. And increased pressure means increased flow. So before the point of resistance, pressure will increase. But after the point of resistance, like up to this portion, pressure will decrease. So this is what it is. So when an arterial vasodilates, and what would happen if there is a arteriolar vasodilatation? That means both efferent and efferent vasodilation. Vasodilation means there will be reduction of resistance and there will be increase of flow. Now this slide, this is very, very important. You can expect question from this slide. So this is actually, don't make it difficult. Okay, this is actually like everything that I have discussed till now. This is just that, just a summary of that. So afferent constriction, what happens if there is a constriction in the afferent arteriole, and what happens if there is a constriction in the efferent arteriole? So first of all, what would happen to the glomerular filtration pressure? So if there is an afferent arteriolar constriction, just a moment. So yeah, if there is an afferent arteriolar constriction, what would happen? Glomerular filtration pressure will drop because blood cannot pass through the glomerulus at all. So definitely filtration pressure will drop. But if there is a efferent arteriolar constriction, that means what? I just told you that if there is a efferent constriction, that blood can pass and blood can enter into the Bowman space. So the glomerular filtration pressure will increase because there is a pressure buildup before the point of obstruction. So this is the point of obstruction. So here the pressure will increase. So glomerular filtration pressure will increase if there is efferent constriction. What would happen to the GFR? So filtration pressure dropping means GFR will drop as well. Here filtration pressure increasing means GFR will increase. Next, what would happen to the filtration fraction? So we know filtration fraction FF. I told you what is the equation of FF. Filtration fraction equal to GFR divided by renal plasma flow, RPF. GFR by RPF. So here GFR is dropping, renal filtration pressure is same as RPF, same thing, RPF. Glomerular filtration pressure or renal plasma flow is the same thing. So both GFR and RPF is dropping. So filtration fraction will remain same. because both numerator and denominator is dropping, so it will remain same. But in if there is a efferent arteriolar constriction, then what would happen? If efferent arteriolar constriction, GFR will increase, renal plasma flow will decrease. Why renal plasma flow will decrease? If there is a efferent constriction, let me show you here. If there is a efferent arteriolar constriction, GFR will increase because the glomerular filtration pressure is increasing. But why renal plasma flow is decreasing? Because renal plasma flow will happen in one cycle. That means that blood has to come through afferent, then pass through the capillaries network, and then come out through the efferent. But here is the obstruction. So blood is not being able to come out through the efferent capillary. So renal plasma flow will decrease. So since the numerator is increasing and denominator is dropping, the filtration fraction will increase. And lastly, the renal plasma flow or RPF. So renal plasma flow is also dropping if there is a afferent constriction, and in efferent constriction also renal plasma flow is dropping, because told you renal plasma flow means blood has to go inside the afferent, pass through the capillaries, and then it has to come out through the efferent. So since there is a if there is a constriction in the afferent, then blood cannot go through the efferent at all. Like blood cannot start going through the way. So this is why RPF will drop. And if there is efferent constriction, same thing. Blood cannot pass out. So also RPF will drop. So this is all. So it's actually very easy. Just you have to understand the basic regarding this. That's what I told you, that for physiology you don't need to memorize a lot of things. If you just understand the basic, then like there is very little thing that you need to memorize. Next, we'll move into creatinine clearance. So creatinine clearance, what is creatinine clearance? So clearance means volume of plasma that is clear of a substance per unit time. That means a plasma, uh, if a plasma contains a certain thing, we need to get out of our system. So that cleaning process per unit time is called clearance. And we use this clearance. Why do we use it? We use it to assess the renal function. So there are 4 parameters for estimation of clearance, and these parameters are this material. We use creatinine in real life. We use creatinine clearance in practical life we use, or clinical life we use creatinine clearance. But in academically, or like people who does research, they use inulin. Inulin is not used in clinical practice. Inulin only used in for some research purpose or drug trials like this. But in clinical practice we use creatinine clearance. So this creatinine clearance, why are we using creatinine? This is one question. And another question is, to use a substance for clearance, this substance has to pass all these 4 criteria. What are the 4 criteria? The substance has to be freely filtered, the substance cannot be reabsorbed or secreted, cannot be metabolized, and must not alter GFR. And creatinine is, we know it produces from the muscle metabolism, and only very little amount is secreted, but rest of the parameters are usually met. And this is why we use creatinine in clearance. And another thing is about MDRD equation. So MDRD equation, it's a big equation and you don't need it because I haven't seen any recall, but these are recalls. Okay, like what are the parameter of clearance? This is important. And regarding MDRD equation, yeah, MDRD equation, it is basically a equation that is used to determine this clearance and everything. You don't need the equation. No, I don't think it's important for exam. But just know this thing, that is this MDRD equation uses plasma creatinine to estimate GFR, and it depends upon age, sex, and race. Just know this line, that is enough. Next, we will move into the regulatory mechanism. So, regulatory mechanism of plasma osmolarity. We know that our body has a criteria or a mechanism which is called homeostasis. And what does it mean? It means that it wants to keep a optimum environment in the body, no matter what happens. Like you are dehydrated, but it will do everything to reserve the blood volume, and this is called regulatory mechanism. So we have discussed about different regulatory mechanism. Today we are going to discuss about regulatory mechanism of plasma osmolarity. So in plasma osmolarity, osmolarity means that our body has solute and our body has like water. So they always maintain to measure the osmolarity. We need two things, one solvent and another solute, and the solute particles will exert a pressure which is called osmolarity. So now this plasma osmolarity, there are some regulatory mechanism for plasma osmolarity. Number one is osmoreceptors. So in our body, we have some osmoreceptors which can be found in the hypothalamic nucleus, supraoptic hypothalamic nucleus. So when there is some situation and the body plasma osmolarity of the body fluid has increased, that means what? That means that our body is dehydrated. Osmolarity increase means there is increased solution, but the increased solute, but the water has decreased, and this is why osmolarity has increased. So when there will be increased osmolarity of body, what would our body do? The osmoreceptors which are present in the hypothalamic nucleus, they will send a signal to the hypothalamus, to the pituitary, to produce ADH, antidiuretic hormone. Antidiuretic hormone, ADH or vasopressin. Same thing, different name. So we know this ADH is secreted from posterior pituitary. So osmoreceptor will send signal to produce ADH, and the function of ADH is to do water reabsorption. So if I am reabsorbing a lot of water, then what is going to happen? The osmolarity is going to drop. So this is how the body is maintaining an optimum osmolarity as much as possible. Next is the baroreceptor. So like osmoreceptor, there are some baroreceptor. Osmoreceptors are sensitive to osmolarity. Baroreceptors are sensitive to pressure. Baro means pressure. So baroreceptors are sensitive to pressure. So if there is any fall of blood pressure, whether due to blood loss, hypovolemia, vomiting, dehydration, whatever it is, everything like blood loss, hypovolemia, volume loss, water loss, anything will ultimately do what? Ultimately will fall the blood pressure. So what would happen? This baroreceptor, their impulse will be taken through the 910 cranial nerve, and it will carry the stimulation of ADH production release. And once ADH is production happens, there is water reabsorption. And if water is reabsorbing, we are reabsorbing a lot of water, then blood pressure will increase. Next is the thirst mechanism. So we have a thirst center which is present in the anterior lateral region of hypothalamus. And this thirst center is, it responds to the osmolarity of the body fluid. So if the osmolarity is increased, so that means that body is sensing that we need some water to balance the osmolarity. So that would stimulate that person thirst center, and we will become thirsty and we will look for water. When we will drink water, so body water volume will increase, osmolarity will balance. Next, so these are called regulatory mechanism for plasma osmolarity. Next, we will move into another very important autoregulation, which is called renal autoregulation. Now, what is renal autoregulation? Renal autoregulation means same thing. I told you, like every minute, we know that renal plasma flow is 600 per minute. That is huge. 600 ml of blood per minute. There are 600 ml of blood that is passing through the kidney per minute. Okay, so this renal plasma flow, this maintenance of renal plasma flow, if it is dropping for some reason, our body initially, sorry, yeah, initially our body always will, just a moment, yeah, so initially for some reason, suppose like a person is having condition like hypovolemia or shock, a person goes into shock. Okay, initially our body will try its level best to maintain this renal plasma flow, RPF. Yeah, so initially our body will try to fight back and try to maintain the optimum RPF. But ultimately, if that person enters into shock, then body cannot. So the mechanism that the body is going through to maintain the renal plasma flow is called renal autoregulation. So despite the change of systemic arterial pressure, body will fight back to maintain the renal plasma flow, and this is called renal autoregulation. There are four mechanisms through which this renal autoregulation happens. Number one is myogenic mechanism. Number two is tubuloglomerular feedback mechanism. This is the tubuloglomerular feedback mechanism. Another thing I have been constantly telling you guys, that whenever you are making note, or whoever has the access to the all our notes, which we later post in the drive, so whoever have the access and you are making your own notes, it is always best first of all to make your own notes. And whenever you are making your own notes, do this one thing, like here I got tubular feedback mechanism in the first slide. I also got tubular feedback mechanism. What did I get there? I get there that this tubular feedback mechanism is done by a special type of cell, which is called macula densa. So just write it here. Where is the site of macula densa? Site of macula densa is thick ascending limb of loop of Henle and DCT. So just write it here so that you get two division in a same topic. So anyways, so there are four feedback mechanism: myogenic, tubuloglomerular feedback, neuronal, and hormonal. And we will be discussing about all of it thoroughly. But before that, I want to show you the blood flow of kidney. So kidney blood flow will start from renal artery. And as I have already mentioned, that kidney receives about 20% of total cardiac output. From renal artery, I will go to the arcuate artery. Arcuate artery will convert into afferent arteriole. Afferent arteriole, we know there is a afferent arteriole becomes efferent arteriole, but in the middle there are glomerular capillaries. So from efferent arteriole, we have peritubular capillaries. From peritubular capillaries, we have vasa recta. Vasa recta will drain into arcuate vein, and arcuate vein will drain into renal vein. This is very easy flowchart. Just go through it once. So this portion we already know, like the afferent, glomerular capillary, efferent, and renal will become arcuate. Again, arcuate vein will become renal vein. Just you have to remember these two steps: peritubular capillaries and vasa recta. Anyways, now I will move into the all four autoregulation that kidney does to maintain the renal plasma flow despite the blood pressure change. So we will start with myogenic autoregulation. So the name will say it, like don't bother much. Myogenic means what? Myo means muscle. Myogenic means muscle. So that means something with the arterial muscle. So what would happen in myogenic autoregulation? Increased arterial blood pressure. If there is any increase in the arterial blood pressure, then afferent arterial blood pressure will also increase. and that is going to cause a stretch to the arterial wall. If the pressure is increasing, that is causing some stretch to the arterial wall. And in the arterial wall muscle, there is some receptor. So there is going to be a positive stimulus in the myogenic stretch receptor. When there is a positive myogenic stretch receptor, that is going to open the voltage gated calcium channel. And due to the opening of the voltage gated calcium channel, calcium will influx from extracellular fluid to vascular smooth muscle. And whenever calcium is entering inside a smooth muscle, that means only one thing: contraction. So there is going to be contraction of vascular smooth muscle, and contraction means vasoconstriction. And if there is a vasoconstriction, then that would minimize the changes in the afferent arterial blood flow and minimize the change in GFR and renal blood flow. So that means if there is, for some reason, arterial blood pressure has increased, that is going to cause the arteriolar vasoconstriction, so that it will maintain the optimum blood flow. Blood pressure increase means a lot of pressure, like it is creating high pressure, but then it will contract the arteriole, and ultimately that would minimize the change in GFR and renal blood flow. That means that no matter what is the blood pressure is, if there is a drop of arterial blood pressure, opposite thing will happen. So through the myogenic autoregulation, the renal capillaries, they are um, just working according to the blood pressure. If the blood pressure is increasing, there will be constriction, and there will be optimum entrance of the blood or the blood flow. So this is all about myogenic autoregulation. Now we will move into tubular-glomerular feedback mechanism. So tubular-glomerular feedback mechanism, already mentioned, it comes from that macula densa. There are some special cell in the macula densa which can be found in the junction of thick ascending limb of loop of Henle and DCT. So what would happen in this feedback? Tubulo-glomerular feedback. So if the mean arterial pressure, for some reason, again, high blood pressure, so mean arterial pressure has increased. Mean arterial pressure has increased means renal blood flow has also increased. So GFR will also increase. So if the GFR has increased, that means there is going to be a high delivery of sodium to macula densa. And I told you this macula densa function is to sense the sodium content of blood. So if there is a high delivery of sodium to the macula densa, that is going to, this macula densa is going to activate the tubulo-glomerular feedback mechanism, and in resultant to that, there is going to be secretion of adenosine and ATP. And this adenosine and ATP secretion, they will work as a vasoconstrictor. So they will do the vasoconstriction. So ultimately, again, decrease renal blood flow and GFR. And similarly, the opposite thing will happen if there is decreased mean arterial pressure. That means low delivery of macula densa to the low delivery of sodium to the macula densa. Then there is going to be vasodilatation, and that is going to increase the renal blood flow and GFR. So the point is, no matter what the blood pressure is, ultimately through this feedback mechanism, they are maintaining an optimum renal blood flow, or RPF, renal plasma flow, and GFR. And optimum renal plasma flow and GFR. So that is all about tubulo-glomerular feedback mechanism. Next is the neural regulation. Neural means neuronal. So neural is for kidney, it is a viscera, and visceral neuronal activity is always autonomic. Autonomic means sympathetic and parasympathetic. So in sympathetic, there is going to be sympathetic is going to innervate the afferent and efferent arteriole. but the effect is greater in the afferent arterial, resulting in vasoconstriction. Because we have already discussed this during basic cellular when I taught you the autonomic nervous system. In the kidney, the sympathetic causes vasoconstriction. Sympathetic causes vasoconstriction in most of the blood vessel. So sympathetic will result in vasoconstriction, and if there is vasoconstriction, then the blood volume will decrease, GFR will decrease. And in parasympathetic, parasympathetic is neurotransmitter is acetylcholine, and parasympathetic acetylcholine causes release of nitric oxide from endothelial cell. This vascular endothelial cells has nitric oxide. They can secrete nitric oxide. So acetylcholine, parasympathetic neurotransmitter is acetylcholine. Acetylcholine will cause secretion of nitric oxide from endothelial cell, and nitric oxide will do what? Vasodilatation, because we know nitric oxide is a vasodilator. So that is neuronal. Next, we'll move into hormonal regulation. So in hormonal regulation, um, hormonal means there are quite a few substance, either hormones or neurotransmitter. They acts as a they have different function. These hormones would include norepinephrine, angiotensin 2, prostaglandin, nitric oxide. So nitric oxide used for vasodilatation, prostaglandin. They secrete in different situation according to the need. Okay, so hormonal regulation is nothing but just different hormone that they have different effect on the blood vessel. So norepinephrine is a vasoconstrictor. It increases sympathetic tone. Angiotensin 2 is a powerful vasoconstrictor. Prostaglandin, it reduces vasoconstrictor effect of sympathetic nerve and angiotensin. That means prostaglandin is a vasodilator, nitric oxide is a vasodilator. So hormonal for your so the thing is, regarding hormonal regulation, we need to know about all of the vasodilator and vasoconstrictor. So I have combined all the vasodilator and constrictor here. Okay, so vasodilators are nitric oxide, prostaglandin, bradykinin, low dose dopamine, adrenomedulin, natriuretic peptide, ANP, not AND, ANP, calcium channel blocker. These are vasodilators. And vasoconstrictors are angiotensin 2, vasopressin, endothelin, NORAD, high dose dopamine, adenosine, thromboxane 2. So first of all, this is very, very important, very, very important recall. Even if you start solving success, you will get this vasodilator vasoconstriction, at least 20 question in the success from this vasodilatation and vasoconstrictor. So you have to memorize it. You can make mnemonics. I don't have any. I could remember it as it is, but if possible, make a mnemonic for it. But you have to memorize what are the vasodilators, what are the vasoconstrictors. Next, we will move into our today's most important topic, which is renin-angiotensin system. So first heads up about renin-angiotensin system is this whole topic is a recall. They can ask you anything from renin-angiotensin system. So I am not going to mention, well, this is a recall, this is a recall. No, everything is very, very important from renin-angiotensin system, and it is very easy. Like if you pay attention and if you understand it, you don't need to memorize anything, like maybe very tiny bits of it, but not a lot of things. So everything is recalled from renin-angiotensin system. Okay, so let's move here. So we know that renin is secreted from Jg cell or granular cell, and first of all, renin is a catalytic enzyme. Next is the stimulation. So stimulation means what are the stimulation that will cause Jg cell to secrete renin. So first stimulation is decreased renal perfusion. If there is a decrease in the renal perfusion or renal blood flow, that is going to cause renin secretion. Just a moment, guys. Okay, all right. So that is going to cause renin secretion, And the mechanism is, we have already discussed, myogenic autoregulation. So if there is decreased renal perfusion, that is going to activate myogenic autoregulation, and that is going to cause renin secretion. Next is the change in the volume composition of tubular fluid reaching the macula densa. What is it? This is nothing but tubuloglomerular feedback mechanism. So tubuloglomerular feedback mechanism also activates renin secretion. And last is the sympathetic stimulation by sympathetic nerve. So this is the neural. So whenever there is a sympathetic stimulation, that will also stimulate renin secretion. So three stimulants, one is the myogenic, another is the tubuloglomerular, another is the sympathetic stimulation. So all of these things will secrete renin from JG cell. Next, we'll move into renin angiotensin system. So renin angiotensin system, as I have already mentioned to you, that when there is renal blood flow, decreased in the renal blood flow, that means myogenic, or decrease in the sodium, that means tubuloglomerular feedback, or sympathetic secretion, JG cell will get stimulated and JG cell will secrete renin. Now, what is the function of renin? So this renin will do what? It will convert angiotensinogen to angiotensin 1. Now, the only thing you need to know about angiotensinogen is that it is produced in liver. This angiotensinogen, it is produced in liver and it circulates in the blood. It is a hormone and it is an inactivated hormone. So the first function of renin is to activate this inactivated angiotensinogen to angiotensin 1. Now this angiotensin 1 is like a interim, it's in an interim state. It is not completely activated. So this angiotensin 1 will get activated to its complete active form, which is angiotensin 2, by angiotensin converting enzyme. So this is a angiotensin converting enzyme, and this enzyme we can find it in the lungs. This angiotensin converting enzyme is founding in the can be found in the lung, and this angiotensin 1 will become angiotensin 2. This is the most activated form. And this angiotensin 1 is, first of all, it is a, as I have already discussed, this angiotensin 2, angiotensin 1 is the inactivate. Angiotensinogen is also inactivated. So angiotensin 2 is the active form and it is a very powerful vasoconstrictor. So it is a powerful vasoconstrictor, but it won't stop here. It won't stop here. It will do what? This angiotensin 2, one action it will exert is the vasoconstriction, powerful vasoconstriction. And it has another action, which is to release aldosterone. To release aldosterone from where? From where? Aldosterone releases from where? Aldosterone releases from adrenal gland or suprarenal gland, specifically from zona glomerulosa. Specifically from zona glomerulosa. So angiotensin 2, this angiotensin 2 will stimulate the zona glomerulosa, which is the adrenal cortex, and ultimately it will release aldosterone. Next, what would happen? What is the function of aldosterone? The function of aldosterone is to increase sodium reabsorption and water reabsorption. So if sodium, it has reabsorbed sodium and water, ultimately what is going to happen? Plasma volume will increase, cardiac output will increase, blood pressure will increase. And by the action of vasoconstriction, again, blood pressure will increase. And this is nothing but renin angiotensin system. Now, there are few things that I want you to know here. That is, I want to give you a clinical correlate right here. That is, clinically, we use two drugs very frequently. One is called AC inhibitor, another is called ARB. AC inhibitor means angiotensin converting enzyme inhibitor. So AC inhibitor will work right here. AC inhibitor will block this angiotensin converting enzyme. It will block here. This if you're giving AC inhibitor to someone, it works right here. It blocks the angiotensin converting enzyme. So angiotensin 1 cannot get into its active form, angiotensin 2. Next is the ARB. ARB is where does ARB works? So ARB works in this step, this step right here. This angiotensin 2 stimulates the zona glomerulosa and produces aldosterone. Right here, ARB works. That is angiotensin reversible blocker. This is the angiotensin blocker or angiotensin 2 blocker, whatever you say. So it blocks the potent form of angiotensin 2 and it cannot produce aldosterone in the zona glomerulosa. So this is a clinical correlate, but that is all about renin angiotensin system. Okay, just a moment. All right. So that is all about renin angiotensin system. So I think you shouldn't have any question here. That's all you need to know. We will move into the next topic. Stimulation I have already discussed. If there is fall of pressure or increase of pressure, that is the myogenic decreased sodium, that is the tubuloglomerular, and the sympathetic stimulation, that is the stimulation. Next is, so this is very, very important. Okay, I mean, I shouldn't even need to mention, I already told you everything, every steps from here you need to understand it, and that's very easy actually. Next is the function of angiotensin. So again, another very, very important 3-star slide is function of angiotensin 2. So what is the function of angiotensin 2? Though I have already discussed it. Number one is it is a peripheral arteriolar vasoconstrictor. So it increases peripheral resistance. This is how it increases BP. Next is angiotensin constricts both efferent and afferent arteriole, but efferent constriction is more prominent. So we know that if there is constriction in the efferent, then that increases filtration. And ultimately it is a overall vasoconstrictor. So vasoconstriction means peripheral resistance, increasing peripheral resistance. So the mean arterial pressure will also increase because it will increase total peripheral resistance. Next is the stimulation of ADH secretion. So we know this number 3 I have already showed you here, that how angiotensin 2 stimulates zona glomerulosa and releases aldosterone. So stimulation of aldosterone in zona glomerulosa, but it also stimulates ADH secretion. Don't get confused between ADH and aldosterone. ADH is antidiuretic hormone that comes from posterior pituitary. Aldosterone is a adrenal hormone that comes from adrenal cortex, zona glomerulosa. So angiotensin 2 stimulates both of it. It stimulates ADH, it stimulates aldosterone. So the function of ADH is only water reabsorption. So it will stimulate ADH and it will do the water reabsorption and increase the blood pressure. And it will also stimulate the thirst center. So if it's stimulating the thirst center, that means you are drinking more water. So water is increasing. And also it will enhance the sodium reabsorption by proximal tubule or PCT. So look, like there are completely like 5 or 6 way that it is increasing the blood pressure. Whatever it is doing, angiotensin is doing, It is increasing the blood pressure by either increasing the peripheral resistance by doing the vasoconstriction, increasing the blood pressure, by stimulating ADH secretion, water reabsorption, increasing the blood pressure, stimulating the thirst center, water intake, increasing blood pressure, stimulating aldosterone, water and sodium reabsorption, increasing blood pressure, and also enhance the sodium reabsorption in the PCT. So if sodium, we are reabsorbing sodium, that means sodium, if the sodium content is increasing in the blood, sodium will carry water along with it, increase of blood pressure. So ultimate function of angiotensin 2 is to maintain the blood pressure. So that is all about the function of angiotensin 2. Next, we will move into the aldosterone. So the thing is, I told you that renal and endocrine is very, very interrelated. Like these are the same slide you will get in endocrine as well. So since I'm discussing here, I might not discuss this similar thing there. So pay attention, okay? So now the thing is aldosterone. How does this aldosterone work? I just roughly told you that the function of aldosterone is to water reabsorption and sodium reabsorption. But how? So I will show you how. So first of all, aldosterone, it works in the late distal tubule or late DCT and collecting tubule or CT. So mainly it works in the collecting tubule. Late DCT means like the last portion of distal tubule, which is like starting of the collecting tubule. So how does this aldosterone works? So this is the basal membrane and this is the luminal membrane. First of all, what does luminal membrane and what does basal membrane means? So luminal membrane means that it is a lumen. So it is the lumen. So here we have urine. So anything that will fall into this direction will get excreted or secreted into the urine. And basal membrane means the basement membrane. The basement membrane of the glomerulus. That means anything that will come beyond this line will get reabsorbed into the body. Okay, so if we understand this, then next let me explain this thing. So how this aldosterone works. So first of all, this aldosterone in the basement membrane, in the basolateral membrane, there is a sodium potassium ATPase pump right here. So the function of this sodium potassium ATPase pump is to sodium reabsorption. So here you can see that it is the sodium is going into this way. So sodium reabsorption. So we are reabsorbing sodium. That means we are taking it in, we are just again taking it up into the blood. And in exchange of sodium, in this sodium potassium ATPase pump, potassium is going out. Going out where? Luminal. Luminal means what? Urine. So potassium is being secreted in the urine. So sodium, we are reabsorbing sodium and we are excreting, or not excreting, secreting potassium in the lumen or in the urine. Next, what is happening? We have water and carbon dioxide here. So along with the carbonic anhydrase enzyme, this is carbonic acid is further divided into bicarbonate and proton. So proton is getting secreted. Proton is getting secreted, but the bicarbonate is getting reabsorbed. Not reabsorbed, actually, it is actually produced. Like there was no bicarbonate right here, right? So this guy bicarbonate, we have produced new bicarbonate. So if we are producing bicarbonate and if we are losing proton, what is this term? Is it acidosis or is it alkalosis? Definitely, it is alkalosis. Alkalosis means base production. So we are producing base, but we are not only producing base, we are losing acid. Proton is acid. So metabolic alkalosis. Why metabolic? Because renal is metabolic. Respiratory, I will today I have also include ABG in our today's class. I am not sure if I will be able to complete or reach through the ABG or not. If not, I will discuss about ABG in the next class along with endocrine. But like I will give you a complete overview of ABG. Lot of you, I know, use ABG for a daily basis in clinical practice, but some of you may have a long clinical gap or long study gap, and maybe you're confused with the ABG. This is why it is very essential to know about the ABG, and also it's a recall topic. The ABG, complete ABG is a recall topic. So I will discuss if I get time. But my point is now that uh, if we are doing something with the lung, that is the, if we're retaining carbon dioxide or washing out carbon dioxide, that is called respiratory. If this function is going through the kidney, that is metabolic. So since it is a, we are now learning renal, so it's a kidney function and there is bicarbonate production, so it is called metabolic alkalosis. Next is water. So since sodium, we are reabsorbing sodium, and whenever sodium goes, it carries water along with that. So there is going to be water reabsorption as well. So this is all about the function of aldosterone in the late distal tubule, mainly in the collecting tubule. So mainly in the collecting tubule, the function of aldosterone is to reabsorb sodium, number one. Number two, reabsorb water. Number three, secrete potassium, secrete proton. Number five, production of bicarbonate, and working towards metabolic alkalosis. So if you understand this, next we will move here. So stimulation of aldosterone production I am discussing, but first just look here. So this is what I have just mentioned in the, and right here, this is same thing. So sodium, we will reabsorb sodium, so ultimately in the body sodium content will increase. Potassium we are secreting, so in the body potassium containing plasma potassium is reducing because we are secreting it in the urine. Secretion means what? I told you, secretion means we are secreting it in the urine. That means that is coming out of the body. So that means potassium, plasma potassium will fall. Proton, again we are secreting, so proton is an acid, so acid losing means metabolic alkalosis. Bicarb we are producing, also metabolic acidosis. Water we are reabsorbing, that means increase of volume. So that is the function of action of aldosterone. Very very important recall. Okay, next is the stimulation. What are the stimulation of aldosterone production? So one stimulation of aldosterone production we know is the angiotensin 2. We know whenever there is angiotensin 2, angiotensin 2 will stimulate the zona glomerulosa and there will be release of aldosterone. This part we already know. Next, there are some other factor that stimulates aldosterone production, which will include if there is a reduction of ANP, atrial natriuretic peptide. I will discuss about it thoroughly, but this is another hormone that releases from the atrial smooth muscle. So if there is a reduction of ANP, that would also stimulate aldosterone production. If there is a plasma potassium concentration increase, if there is a, because we know that function of aldosterone is to reduce plasma potassium. So if there is an increased plasma potassium, that would also stimulate aldosterone production, because the body always want to maintain a homeostasis, and increased potassium can cause a lot of problem, cardiac arrhythmia. So body will secrete aldosterone, aldosterone will secrete this potassium into the urine and will move this potassium out of the body. Next is the decreased sodium concentration. So Same thing, the function of aldosterone is to increase sodium reabsorption and increase sodium content in the overall body. So if there is decreased concentration, again aldosterone will reabsorb the sodium and it will increase the sodium concentration. And this aldosterone works in the two area, that is the late distal tubule and collecting tubule, DCT and CT. This is also recall, like everything is recall here, right here, regarding renin and aldosterone. So it acts on DCT and CT. So next thing, we will move into the ANP. So as I just mentioned, ANP is a hormone, atrial natriuretic peptide. So atrial, the name suggests, the name will say its action. A for atrial. Atrium means what? Atrium means atria of the heart, right? So it is comes from heart. And natriuretic, sorry, sorry guys. Natriuretic means sodium. Peptide is the protein. So ANP releases from cardiac myocyte, response to the atrial stretch receptor. When large volume of blood enters into the heart, it enters into the heart, this ANP is released, and it is an inhibitory hormone. This ANP, it is a mainly a inhibitory hormone. Whenever there is a suppose a situation when someone is having a volume overload, that means a lot of volume has stagnant inside the body. So that is going to do what? This volume overload will going to stretch the atrial receptor, because there was not supposed to so much big volume going into the atrium, but for some volume, for some reason, for some pathology, there is volume overload. So this ANP, so the atrial myocyte, it will produce ANP, and this ANP is an inhibitory hormone. It inhibits a lot of things. I will tell you what are the things. Mainly it inhibits or antagonizes renin angiotensin aldosterone system. And as we just have gone through renin angiotensin aldosterone system, the function of renin angiotensin aldosterone system is to increase plasma volume, increase cardiac output, increase blood pressure. So this ANP will inhibit the whole renin angiotensin aldosterone system. So ultimately, low plasma volume, low cardiac output, low blood pressure, and our aim will be achieved from here. So the function of ANP. Function of ANP is to, main function is to reduce sodium, reduce water, reduce blood volume, so that atrial muscles are not again stretched, so much stretched. Next is the vasodilatation of afferent and vasoconstriction of efferent arteriole. So if there is a vasodilatation in the afferent and vasoconstriction in the efferent, what would happen? Though I have discussed this multiple times, again, let me show you. Vasodilatation of afferent. That means blood, so much blood, a lot of amount of blood will pass through the afferent and will come into the capillaries. But there is a constriction of the efferent arteriole. So blood has come through the afferent. Due to the vasodilation, big volume of blood has come through the afferent and then reached into the capillary, glomerular capillary, but it cannot escape through the efferent way. So ultimately, they have only one way, that is to pass through the glomerular Bowman space or glomerular membrane, and it will ultimately, it will excrete as a urine, so that the volume is not coming back in the body. So this is the main aim for the ANP. So these are the function. Another function is, I told you, inhibition. So it will inhibit each and everything that increases the blood volume or that increases the blood pressure. So it will inhibit renin. It will inhibit renin angiotensin aldosterone system. It will inhibit aldosterone. It will inhibit ADH secretion, ADH action. It will inhibit sodium reabsorption in collecting tubule. It will inhibit sodium reabsorption in the distal tubule through ENaC. One more thing I forgot to mention about what is ENaC. ENaC is nothing but this. ENaC stands for epithelial, Na for sodium, C for channel. So this is ENaC. This cell, here we have a sodium channel, right? The sodium potassium ATPase channel. So this is nothing but ENaC. Epithelial sodium channel. Since it is in the basement membrane epithelial cell, this is called epithelial sodium channel. So ANP will inhibit sodium reabsorption in the DCT through ENaC. So it will inhibit everything. So the main function of ANP is to inhibit everything that increases blood volume and increases blood pressure. And the main function of ANP is to reduce the blood volume and reduce the blood pressure. So we are done with that. Now we will move into another hormone, which is ADH. As I have mentioned to you already, that the function of ADH is to do the water reabsorption, right? So that is the only function of ADH. ADH stands for anti-diuretic hormone. Just look at the name, okay? Anti-diuretic. Anti means against. Diuresis means what? Diuresis means urine, producing urine. Diuresis, the word diuresis means production of urine and remove of extra whatever water or any material, any particle through the urine. It is called diuresis. So ADH stands for anti-diuretic urine. That means we cannot produce urine. It has another name, which is vasopressin. ADH, antidiuretic, vasopressin. So its function is to increase the collecting duct permeability to water and medullary portion of urea. So the function of antidiuretic hormone only works into the collecting duct. Aldosterone works in the distal DCT and collecting duct or collecting tubule, same thing. But ADH only works into the CT or CD, collecting duct or collecting tubule, and it increases the permeability. Suppose this is a collecting duct and collecting duct has some pores in it. So what this ADH does is it increases this size of the pores. So what would happen? More water cannot pass, so more water will get reabsorbed due to the increase of the permeability of collecting duct. So how it works, if there is a decreased volume into the body, hypothalamus will get stimulated. Hypothalamus will stimulate the posterior pituitary, and posterior pituitary will release vasopressin or ADH or antidiuretic hormone. So one function is kidney will reabsorb water into the collecting duct. If kidney is reabsorbing water, that means blood volume is increasing, blood pressure is increasing. Also, it has another name, an antidiuretic, which is vasopressin. Vasopressin means what? Vaso means vessel, pressin means press. That means it is a vasoconstrictor. If you forget about it, like is vasopressin vasoconstrictor or vasodilator, just look at the name. Vasopressin means it is pressing the vessel. That means it is constricting the vessel. So it is a vasoconstrictor. And if it is a vasoconstrictor, vasoconstriction means increasing peripheral resistance, ultimately increasing arterial blood pressure. So that is the function of ADH. Next, we will move into the most important topic of another most important topic of our today's class, which is called tubular transport. Like numerous recalls has been from this topic. Every line is a recall. I won't mention this is recall, this is recall. No, every line is recall. You need to know everything about tubular transport. So first of all, we will start with the PCT. So PCT reabsorption, it reabsorbs 66% sodium, potassium, chloride, water. It reabsorbs 100% of glucose by SGLT transport. It reabsorbs 80% of bicarbs. It reabsorbs all protein, amino acid, ketones, and the basal sodium potassium ATPase creates a gradient for movement of sodium in and out, and it secretes drugs and metabolites. You just have to memorize it. Next is the what are the transport mechanism, sodium transport mechanism in PCT. So we have SGLT, sodium glucose co-transport, sodium proton exchanger. It is an antiporter. 80% of sodium gets reabsorbed through it. This is very, very important. 80%. So I mentioned about like 66% sodium gets reabsorbed in the PCT. This ratio is actually 66 in some place. In some place they have mentioned about 80%. So make sure you're open for both. And they won't give you two option, two of the same option. So 80% of the sodium gets reabsorbed into the sodium proton exchanger through this channel. And there is another transport mechanism which is called chloride driven sodium transport. So this is all happens in the proximal tubule. Next, I want to discuss about another important topic which is called Tmax, glucose Tmax. Why? Because here I told you that 100% of the sodium, glucose gets reabsorbed into the PCT by SGLT transport. So that means in the urine, for a normal person, urine should never contain any sort of glucose. Urine should never contain any sort of glucose. Why would urine contain any glucose? Because here they are saying that in the PCT, through the SGLT transport, 100% glucose gets reabsorbed. So there is no secretion, no excretion of glucose in the urine. So to understand that, you need to understand this glucose Tmax. What is glucose Tmax? So glucose Tmax is the maximum rate of absorption of a substance by any transporter in the tubular transport. That means that in the PCT, 100% glucose should get reabsorbed. But but that is for normal individual, normal person who has a normal blood sugar. But if someone have excessive amount of blood sugar, like an uncontrolled diabetic patient, for this patient we find glucose in the urine. We call it glycosuria. So why do we find glycosuria in diabetic patient then? We find it because of the Tmax. So there is a threshold. Up to that threshold, there shouldn't be any glucose into the urine. But if we cross that threshold, then glucose will start appearing into the urine. And this is what happens in diabetic patient. We call it glycosuria. So this is what the Tmax is. Tmax is nothing but the threshold of glucose. That up to that, no glucose will appear into the urine. But if we cross that, then glucose will appear into the urine. So normally, this renal threshold for glucose is 11 millimole per liter. It is normally, like practically, but theoretically it is 16 millimole per liter. So this is why it is called splay. Splay means like destruction, deviation. Theoretically there was supposed to be 16 millimole, but what is diabetes? Diabetes means blood sugar more than 11, that we all know, right? So why 11? Because if we go beyond 11, then glucose will start appearing into the urine. So there is a deviation from theory to practical implementation. This is why it is called splay. But the thing is, renal threshold for glucose is 11 millimole per liter. Okay, so if in real life, after 11 millimole per liter, glucose will start appearing into the urine. Next is, so we are done with PCT, proximal tubule. We have done the tubular transport of proximal tubule. Next is the loop of Henle. So as I have already showed you that loop of Henle has three parts: thin descending, thin ascending, and thick ascending. So the thin descending limb, it is very permeable to passive water transport. So it has the thin descending limb, it is very thin, and it has very few mitochondria. So there is no active transport happens there, because we know to run an active transport we need energy. Just a moment, guys. I need to connect the charger. Just give me 1 minute. Yeah, done. So, loop of Henle. Yeah. So, the first part of loop of Henle is the thin descending limb. Thin descending limb, it is very permeable to passive water transport, but it has few mitochondria, so there is no active transport happens, and this is why it is low permeability to solutes, because solute water can pass through passive transport, but to transport solute we need some active transport, either through sodium potassium ATPase or any sodium SGLT pump. So we need energy for active transport. Since in the thin descending limb of loop of Henle there is no mitochondria, few mitochondria, so active transport does not happen, but it is permeable to water. Next is the thin ascending limb. So thin descending, next is the thin ascending limb. So in the thin ascending limb, it is impermeable to water. So recall, but like all of it is recall, but again, like this one is a very important recall, that the thin ascending limb, it is impermeable to water, it is impermeable to water but highly permeable to the solutes, sodium chloride and urea. That is like opposite to the thin descending limb. Thin descending limb was permeable to water but impermeable to solutes, and the thin ascending limb is impermeable to water and highly permeable to sodium chloride and urea. Next is the thick ascending limb, then it will get thick. So thick ascending limb is the junction of inner and outer medulla. Yes, because I showed you in the first picture that the let me show you again. So basically right here, this was the thin descending limb, this was the thin ascending limb, which is impermeable to water but permeable to solute, and this is the thick ascending limb, and this thick ascending limb is the junction between cortex and medulla. Okay, all right. So it contains multiple mitochondria. So since we have a multiple mitochondria here, that means there are possibility for active transport. So there is in the thick ascending limb, there is active transport of sodium chloride by sodium chloride, sodium potassium 2 chloride symporter or co-transporter. This is very, very, very important, guys. I cannot emphasize enough. Why is that? Because of a clinical importance, because of a clinical correlate. The clinical correlate is, we all have heard of the name of loop diuretics. Like loop diuretics, what is a loop diuretic? Furosemide is a loop diuretic, right? So this loop diuretic works in this channel. It blocks this channel. So they can either give you question with clinical correlate, or they can ask you about the name of the channel. So this sodium potassium 2 chloride co-transporter is present in the thick ascending limb, and it takes part in active transport of sodium and chloride, and it is impermeable to water. So only the first part is permeable to water and the last two part is impermeable to water. The function of loop of Henle is to reabsorb the 20% of sodium and water, the remaining 20%, because 66% to 66 to 80% was transported by, where is it? 66 to 80% was reabsorbed through the PCT. So 66%, not 80. This is like there is variation. In some places in success, maybe they have mentioned 75%. Please have a look. So 66 to 75% sodium and water gets reabsorbed through PCT. So the remaining 20%, is reabsorbed through loop of Henle, water and sodium. and it adds urea to the tubular fluid, and it involves in urinary concentration and dilution. So we're done with the loop of Henle. Now we will move into the distal convoluted tubule, or DCT. So DCT will reabsorb the remaining 5 to 10% of filtered sodium, and it will reabsorb 45% of filtered water. It will reabsorb of urea, and it will take part in secretion of proton and potassium. Just a moment, guys. There has been a mistake. That is, and the mistake is not 45%. Just a printing mistake. Please make sure you correct this. This is 15%. 1 5. 15% of filtered water. Anyways, so in the distal convoluted tubule, what are the things we can find in distal convoluted tubule? So first of all, ENaC. About the ENaC, ENaC is in the late distal tubule, not in the main distal tubule. ENaC, we find ENaC in the late distal tubule and in the collecting duct. But what are the channel we can found in the early distal tubule? So this is a early DCT cell. What happens in early DCT cell? In early DCT cell, one important transporter we have is a sodium chloride symporter. So this is a sodium chloride symporter. Symporter means same direction. I have already discussed what is symporter, what is antiporter. So through sodium chloride symporter, there will be entry of sodium and entry of potassium. And also there is a sodium potassium ATPase pump. We already know about the function of sodium potassium ATPase pump. Also there is 3 sodium calcium 1 calcium antiporter. This is very, very important, this 3 sodium 1 calcium antiporter. And the function of this sodium calcium antiporter is that calcium actively extracted to the peritubular fluid through this 3 sodium calcium antiporter. There is also a calcium ATPase right here. So these are the channels that we can find in a early distal convoluted tubule. So entry of sodium will be coupled with sodium chloride symporter, and this DCT has low permeability for water and urea. Calcium is actively excreted by 3 sodium chloride antiporter right here. And this also express calcium binding protein, calbidin, which facilitates calcium reabsorption. And also there is inhibition of sodium reabsorption by atrial natriuretic peptide. So I have already mentioned about the function of ANP, that ANP does everything to reduce the blood pressure and blood volume, and it inhibits the sodium reabsorption in DCT. So it also works here. Next, we will move into the collecting duct, CT. So collecting duct has 2 type of cell. First of all, I have already showed this picture to you. It has 2 type of cell: principal cell and intercalated cell. So there are some function of principal cell, some function of intercalated cell. Principal cells has the main ENaC. So the epithelial sodium channel ENaC is present into the principal cell. And the principal cell, it also, the aldosterone stimulates the ENaC. How it works, we already know. The principal cell also helps to express aquaporin, which is a protein to enter water. And because of the ENaC, sodium will enter into the basement membrane by basolateral sodium or potassium ATPase pump. So this is the function of principal cell. So the main function of principal cell is, if I have to like summarize, main function of principal cell is sodium reabsorption and water reabsorption. Sodium reabsorption through ENaC and water reabsorption through aquaporin. This is the function of principal cell. Now, what is the function of intercalated cell? So the function of, this is the intercalated cell, this portion. This portion was principal. So the portion of that is in the intercalated cell, its function is to stimulate aldosterone to work in the proton ATPase pump. So through the proton ATPase pump, proton is secreted, and increased aldosterone will cause metabolic alkalosis by what? By production of bicarbonate and secretion of proton. So we are producing bicarbonate, we are taking it, and we are secreting proton into the urine. That means we are losing acid. Losing acid means alkalosis, and producing alkali is also alkalosis. So this is the function of intercalated cell. So in short, the function of intercalated cell is maintaining of acid base balance, which is metabolic alkalosis. Next is calcium handling. So calcium handling in our body, total serum calcium is 2.25 to 2.6 millimole per liter. Average intake is 1 gram per day, and source is milk, cheese, dairy, yogurt, fish, soya, nuts. This was the recall. Maybe they asked for soya, so the source is a recall. Okay, past recall. Next is the kidney excrete 150 milligram into the urine, and 1% of total is filtered. Rest 99% is again reabsorbed in the body. So calcium gets reabsorbed into the body by active process. 60% out of this 99%, 60% into the PCT, 30% in loop of Henle, and 10% in distal convoluted tube. And calcium is reabsorbed, or the calcium reabsorption is done by a hormone which is called parathyroid hormone. It increases calcium reabsorption at the DCT and decreases phosphate reabsorption at the PCT. You need to know these things, okay? These are important. So parathyroid hormone increases reabsorption of calcium into the DCT and decreases phosphate reabsorption into the PCT. And also another thing is important for calcium handling, which is vitamin D. So 125 cholecalciferol or vitamin D increases tubular reabsorption of calcium and phosphate both. But the main function of vitamin D is at the bone and bone resorption and calcium reabsorption. So main thing is parathyroid will increase calcium reabsorption into the DCT, but parathyroid will decrease calcium reabsorption into the PCT. So that is all about our renal system. Now we have, it's already 1 hour and 53 minutes. ABG. I think we can discuss ABG if you guys can give me 20 to 25 minutes. So let's start ABG. Let's not keep it for endocrine, because endocrine is also big enough. So ABG is about ABG. ABG is really easy, okay? Like, I don't know why some people struggle with ABG. I will try to explain it to you in a way so that you don't need to put a lot of stress in it. So let's start our ABG. So ABG means what? Arterial bad blood gas. So we check quite a few things in ABG. We check pH, we check partial pressure of oxygen, carbon dioxide, and bicarbonate. These 4 things are must. Some advanced ABG report can also give you report regarding potassium, like electrolytes, potassium. Can also, some ABG report can also give lactate reports as well, like the advanced ABG. But these are the must things that we need to check while we're checking an ABG. So pH is calculated, pH of blood is calculated into the body through Henderson-Hasselbalch equation. If you wish, you can remember the equation. We need to know the normal values of all of the variable. So normal pH is 7.35 to 7.45. Partial pressure of oxygen is 11 to 14 kilopascal. Carbon dioxide is 4.5 to 6 kilopascal, which is around 35 to 45 millimeter mercury. Bicarb is 24 to 30 millimole per liter. So these are the normal values. Now I will move into the pH and the compensatory mechanism. So pay attention, okay? So normal pH is 7.35 to 7.45. So normal means 7.35 to 7.45. If it is below 7.35, that is called acidemia. If it's above 7.45, then it is called alkalemia. And if it's between 7.35 to 7.45, that means it is normal, or it can also be a mixed acid base disorder. Like it can also be a situation where there has been a compensation done, and this is why the pH is normal, but you will see some abnormality in CO2 or bicarb. So basically, partial pressure of oxygen is not important to look for acidosis or alkalemia. For this, we don't need oxygen. We just need carbon dioxide and bicarb, just these two variables. Partial pressure of oxygen is very important to look for if there is any hypoxia, if the patient is going into respiratory failure or not, this sort of thing. But for metabolic or respiratory acidosis or alkalosis, we don't need partial pressure of oxygen. So we need just these two things: partial pressure of carbon dioxide and bicarbonate. And now I want you to remember one thing, that is carbon dioxide is a acid, bicarbonate is a base. So partial pressure of carbon dioxide high means acid level is high. Bicarbonate level high means base level is high. Okay. So now if the pH is below 7.35, that means that person is having acidosis. Now acidosis can be two type of acidosis. It can be respiratory acidosis, it can be metabolic acidosis. It can be either respiratory acidosis or metabolic acidosis. So when will I call it respiratory acidosis? When will I call it metabolic acidosis? So I told you that whenever it is about carbon dioxide, it is respiratory. And carbon dioxide is an acid. Whenever it is about bicarbonate, it is metabolic. And it is a base. Bicarbonate is a base or alkali. Base or alkali. So respiratory acidosis means high PCO2. That means carbon dioxide is high because carbon dioxide is an acid. And if the carbon dioxide is, and carbon dioxide comes from what? Comes from respiration. So if the partial pressure of carbon dioxide is high, and also in a ABG picture, you are seeing that pH is very low, below 7.35, that means it is a respiratory acidosis. If the pH is below 7.35, but the partial pressure of carbon dioxide is not high, it's normal or it's low, then you have to check the bicarb. And if you see that the bicarb is low, that means it is metabolic acidosis. So metabolic acidosis, to become metabolic acidosis, bicarbonate has to be low, because if the bicarbonate is high, then it is metabolic alkalosis. Okay. Same thing will happen in the alkalemia. Alkalemia can be respiratory alkalemia or metabolic alkalosis. So metabolic alkalosis. So when will we call it respiratory alkalosis? We will call it respiratory alkalosis. Respiratory means PCO2. So write PCO2. PCO2 is an acid. If PCO2 is high, then it is respiratory acidosis. So in the respiratory alkalosis, PCO2 will be low. And in the metabolic alkalosis, bicarb will be high. So if you understand this, then everything will be very easy. Just this basic you need to know. And I think like all of you already know this. So another thing we need to know, so this is about basic metabolic acidosis, respiratory alkalosis, metabolic alkalosis. So now you need to know about the compensation. What does compensation means? So compensation is done by the opposite. So you need to know this thing, that the compensation is done by the complete opposite term. So if someone is having respiratory acidosis, compensation will be done by metabolic. The opposite of respiratory is metabolic. So compensation will be done by acidosis, so alkalosis. So respiratory acidosis, compensation will be done by opposite. Respiratory opposite is metabolic, acidosis opposite is alkalosis. Same thing, in metabolic acidosis, compensation will be done by respiratory alkalosis. In respiratory alkalosis, compensation will be done by metabolic acidosis. In metabolic alkalosis, compensation will be done respiratory acidosis. So compensation will be done by the opposite term to bring back the pH to normal, because the body wants whether it is metabolic acidosis, alkalosis, whatever it is, the body wants to bring back the pH to normal, to function normally. So now the compensation. So again, the compensation I have already mentioned. If the compensation is by the lung, then it is called respiratory. If the compensation is by the kidney, then it is called metabolic. So uh, lung or respiratory compensation is faster than the kidney or the metabolic compensation, because whenever someone is having suppose respiratory so suppose metabolic acidosis, lung can function very fast. How does lung take part in this acidosis or alkalosis? By either like putting carbon dioxide, retaining carbon dioxide, or washing out carbon dioxide. So lung can work very fast. If you take like 50 very fast breath, then you will retain a lot of carbon dioxide, like you will remove a lot of carbon dioxide within 5 minutes. But to remove a lot of base or bicarbonate, kidney has to take a lot of time to go through all the absorption, reabsorption, blah blah blah, this process, this hormonal mechanism. So this is why lung compensation is faster than the metabolic or kidney compensation. So how lung compensation works, let me give you an example. If someone is having a metabolic acidosis, let me give you an example of metabolic acidosis, can be DKA, diabetic ketoacidosis. In diabetic ketoacidosis, there is ketone body formation, and ketone is a acid. So since ketone is a acid, it is a metabolic acidosis, obviously, because this ketone production, this is a byproduct, or this is a waste product of metabolism. So it is a example of decay, is an example of metabolic acidosis. So in decay, what happens? Lung will remove or wash out PCO2. Lung will remove carbon dioxide by hyperventilation. In decay, we find patient with hyperventilation. You can call it, we can call it also Kussmaul breaths. In that, patient take a lot of rapid tachypnea and a lot of deep breath, followed by shallow breath. So what happens ultimately? If we are breathing frequently and we are doing hyperventilation, we are doing nothing but just removing carbon dioxide from the body, and carbon dioxide is an acid. So carbon dioxide, we are losing carbon dioxide means what? Respiratory. Carbon dioxide means respiratory, and carbon dioxide is dropping, that means alkalosis. So this for in response to the metabolic acidosis, we are replying, or we are balancing it with respiratory alkalosis by doing the hyperventilation and by doing the compensation by the lung. And if there is a and how does kidney compensation works? So kidney compensation means what? Metabolic compensation. So definitely it will be a response to respiratory acidosis. For some reason, someone is having respiratory acidosis. Respiratory acidosis means PCO2. PCO2 is very high. It can happen in any type of respiratory failure. Type 2 respiratory failure, for example COPD, or for example in COPD someone is having COPD, and someone is having carbon dioxide retention and is having respiratory acidosis. So kidney will try to compensate that by urinary acidification, by secreting proton by the nephron, reabsorbing bicarbonate, and production and excretion of ammonium is stimulated. Ammonia is also an acid. So what is kidney doing? It's in response to that. Kidney cannot have any effect on PCO2. So kidney has its effect on bicarbonate. So kidney will produce bicarbonate, and kidney will secrete or excrete acid, and kidney will also excrete ammonia. Ammonia is also an acidic substance. So by this thing, kidney is responding to this respiratory acidosis by doing metabolic alkalosis. So that is all you need to know about respiratory and metabolic acidosis, alkalosis. So I think like you shouldn't have any confusion regarding this. So if you get a ABG report, like that is all for the exam purpose. So in real life, if you get a ABG report, the first thing you are going to look in that ABG report is the pH. If the pH is normal, then you will look if the partial pressure of oxygen, if patient is having hypoxia, you'll obviously see like if the patient is having hypoxia or not. But for looking for acidosis or alkalosis, this thing, we will first check the pH. If the pH is normal, if the pH is low, then we will first check, is the PCO2 high or is the bicarb low? So we will look for the, if is it metabolic or is it respiratory. Same, if the pH is higher, in the higher end, then we will look if the PCO2 is low or if the bicarb is high. We will look for if it's metabolic or if it's respiratory. And this is what we check without any compensation. And compensation, how to know the compensation? Compensation will happen if there is a mixed acid base disorder. So pH can be normal, pH will be normal, your pH will be normal, but still PCO2 will be normal is up to 6, right? But it will be 12. So that means obviously there is something wrong. If the PCO2 is 12, pH cannot be normal. pH uh, mm, should have been lower than 7.35, but the pH is showing that 7.4. So you need to then check the bicarb. Is the bicarb is doing any compensation? And then you can look for it, whether it is metabolic compensation or respiratory compensation. So the next thing is anion gap. It is very, very important topic, recall topic. A lot of recall has come from here. So anion gap is nothing but the sum of measured cation minus sum of measured anion. So the main cation we have is sodium and potassium. So sum of sodium, potassium minus sum of a measured anion is chloride and bicarb. So minus chloride and bicarb. And normal anion gap is 3 to 11 milli equivalent. And this is recall, okay, all of this. So 3 to 11 milli equivalent is normal anion gap. So there is a term called low anion gap and high anion gap. So 3 to if we are measuring our body's total sodium potassium content minus chloride and bicarb content, it should be between 3 to 11. If the anion gap is less than 3, then that is low anion gap. And low anion gap, we found this situation in hypoalbuminemia. Because albumin is negatively charged, in critically ill patient, they are hypoalbuminic, all the critically ill patient, which may decrease the anion gap into normal range, effectively masking wide anion gap acidosis. So low anion gap, we find it in hypoalbuminemia. And there are some situations where there is raised anion gap. Very, very important. Metabolic acidosis with raised anion gap, metabolic acidosis with normal anion gap. Okay, these two charts are very, very important. So low anion gap, we will find it in hypoalbuminemia, but metabolic acidosis plus high anion gap we will find in situation where there will be a raised anion gap. There is a mnemonic for it. It is called mud piles, MUDPILES. Mud piles mark. So mud for methanol, alcohol, U for uremia, D for diabetic ketoacidosis, P for paraldehyde, paracetamol, propylene glycol, I for iron, L for lactic acidosis, E for ethanol, ethylene glycol, S for salicylate, M for metformin, A for alcoholic ketoacidosis, R for rhabdomyolysis, C for cocaine or carbon monoxide poisoning. So either you can remember it with a mnemonic, that is mud piles mark, or uh, you can use both. That is, if you just make a common term from all of this. So methanol, it is an alcohol. Paraldehyde, propylene glycol, these are also alcohol. So alcohol, cocaine, these in this situation we will find metabolic alkalosis with raised anion gap. Next is all acidosis except renal tubular acidosis. So whether it is diabetic ketoacidosis, lactic acidosis, salicylate acidosis, metformin lactic acidosis, all the acidosis we will find raised anion gap with metabolic acidosis except for renal tubular acidosis. Next is infection, uremia, rhabdomyolysis, iron isoniazid. So these are the situation we will find metabolic acidosis with raised anion gap. Now, what are the situation where we will find metabolic acidosis with normal anion gap? So there is also another mnemonic for it. It is fused CAR, FUSED CARS. So fistula, ureteric conduit, saline, endocrine, diarrhea, carbonic anhydrase inhibitor, acetazolamide, aluminium, renal tubular acidosis, spironolactone. So these are the situation we will find normal anion gap. So I told you except renal tubular acidosis. So renal tubular acidosis, in renal tubular acidosis we find metabolic acidosis with normal anion gap. Okay, this is an exception. And also this situation you can use this mnemonic or either this one, both are the same thing. So first is GI loss. If there is any GI loss, whether it is diarrhea, fistula, pancreatic fistula, small bowel fistula. Next is the renal loss, that is renal tubular acidosis, renal dysfunction or failure, hypoaldosteronism, carbonic anhydrase inhibitor, extra chloride. So here is a very important recall, that is excess sodium chloride administration. All of these are important, but excess sodium chloride administration, this is most important. So if in a patient we give, if in a metabolic acidotic patient we infuse excess amount of sodium chloride, then that patient will present with normal anion gap, metabolic acidosis with normal anion gap. So that is all. Okay, we have only 3 slides remaining. So next topic is base excess. So what is base excess? Base excess is same thing as the name suggests. That means we have some extra base. That means how much acid is required to return back to the pH to the normal. Yeah, in some condition, due to some condition, there is some extra base, extra alkali. So to make the pH return to normal, how much acid we need to mix is the base excess. So the definition is amount of strong acid that must be added to each liter of fluid, fully oxygenated blood to return the pH to normal. That is 7.40, because the range is 3.5 to 4.5. So we come in the midline 40. And there are some criteria that pH has to be 7.40. temperature has to be 37 degree or room temperature, and partial pressure of carbon dioxide has to be 40, because the normal is, we know, it is 35 to 45 millimeter mercury, so the middle. So partial pressure of carbon dioxide has to be 40. And the base excess is now the base excess. So if someone is having acidosis, does this person have any base excess? Answer is no. Person is having acidosis. So how can that person have base excess? Because he does not have enough base, and that's why he is having acidosis. He has acid excess, not base excess. So base excess is negative in metabolic acidosis, because already acidosis, so no need to add more acid. Or compensatory respiratory alkalosis, and base excess is positive in metabolic alkalosis, or opposite. What is the opposite of metabolic alkalosis? That is respiratory acidosis. So, or compensatory respiratory acidosis, because compensatory respiratory acidosis is nothing but metabolic alkalosis. Whenever someone having metabolic alkalosis, ultimately there is going to be a compensation by respiratory acidosis. Similarly, whenever there is a metabolic acidosis, ultimately there is going to be a compensation by respiratory alkalosis. So in metabolic alkalosis, there is base excess is positive, because metabolic alkalosis, that person has high base. So base excess is positive. But in acidosis, base excess is negative. Next, we will move into the acidosis and the alkalosis. So metabolic alkalosis. What are the situation we find? What are the causes of metabolic alkalosis? So cause of metabolic alkalosis is, number one is direct loss of proton into the gastric secretion, whether it is vomiting or NG suction. Loss of proton from kidney, where high aldosterone causes sodium reabsorption and proton excretion. So this one we already know from the ENaC. We know the function of ENaC is to secrete proton. Another is Conn syndrome. What is Conn syndrome? Conn syndrome is nothing but aldosterone, hyperaldosteronism. So hyperaldosteronism. So in hyperaldosteronism, what would happen? ENaC will get activated, because the function of ENaC is the same function of the aldosterone. So there will find metabolic alkalosis. Potassium shift into the cell, hypokalemia. If there is a hypokalemia, what happens? In hypokalemia, proton gets inside the cell. So if potassium is going into the cell, that means in the blood there is not potassium, sorry. In hypokalemia, proton gets shifted into the cell. So if the proton is shifting inside the cell, that means that in the blood there is low proton. That means again low acid in the blood, that means alkalosis. And lastly, excess alkali. If there is any IV bicarbonate administration in large amount, or ingestion of antacid, there can also be metabolic alkalosis. So these are the situation we can find metabolic alkalosis. Next is the respiratory acidosis. So respiratory acidosis, what are the situation we can find respiratory acidosis in? If there is any reduced respiratory stimuli into the body, then there will be lack of washout or removal of carbon dioxide. That means if there is any retention of carbon dioxide. We know in type 2 respiratory failure, COPD patient, they do not have respiratory effort. So they have hypoxia, as well as they have carbon dioxide retention in the body, because they are not uh, expiring. Like in inspiration we take oxygen, in expiration we move out the carbon dioxide outside the body. So if someone is having low respiratory stimuli, there will be lack of removal of carbon dioxide or washout of carbon dioxide. So carbon dioxide level will increase, and this is called respiratory acidosis. And the example is anesthesia, drug overload, respiratory depression, COPD, opioid overload, atelectasis, pneumonia. These are the conditions where we can find respiratory acidosis. Next is the respiratory failure. So there are two types of respiratory failure, type 1 and type 2. Both of them have one thing common, that both of them will present with hypoxia. Both of them will have hypoxia. But in type 1, the carbon dioxide is low or normal. But in type 2, there is retention. Type 2 means retention, CO2 retention. Type 1 means no retention, but there is some problem with the respiratory system. That's why hypoxia is there. And partial pressure of carbon dioxide, whether normal or low. But in type 2, there is high partial pressure of carbon dioxide due to the retention or due to ventilatory failure. And the type 1 occurs due to failure of gas exchange or increased oxygen consumption. So this is all about respiratory failure. Next, respiratory alkalosis. When respiratory alkalosis happens, so I have already discussed about this. Respiratory alkalosis means low PCO2. Respiratory means PCO2. Alkalosis means, since it is alkalosis, so low PCO2, because PCO2 is an acid. So whenever there is hyperventilation, there is more washout of PCO2. So PCO2 will drop. PCO2 is an acid. Loss of acid means alkalosis. And the example of respiratory alkalosis is hyperventilation, like anxiety, fear, mechanical ventilation, CNS severe infection, tumor, drug, salicylate, pregnancy. So any situation where there will be hyperventilation, there can be respiratory alkalosis. Next is the serum osmolarity. I have already discussed about serum osmolarity in the basic cellular, how to do the equation and everything, and also the range. A gradient I have also discussed in the last class, so I am not going to discuss today. So with this, we have finished our today's class, which is renal physiology. Now, if any of you have any question, you can unmute yourself and ask the question. Yeah. Does any of you have any question at all? Okay. All right. If no one have any question, then it's already too long. So we will end our today's class, and our next class will be on endocrine physiology. So goodbye, everyone.